Hello friends, today we want to discuss this special integral that is from minus infinity to infinity e raised to the power minus x square dx. Now this function e raised to the power minus x square, if plotted in a graphing softwares like Desmos, you can see easily that this is a bell-shaped curve, and in mathematics we know that the bell shape has a great significance. In statistics, in probability, all this has got a great significance of the bell-shaped curve because it is used to represent the normal distribution function in statistics. The most surprising fact is that from minus infinity to infinity e raised to the power minus x square, when we integrate, what we are doing, we are finding the area bounded by this curve, that is this region. We have to find the area of this region. So surprisingly, you will see that the area that is obtained is nothing but root pi. The area covered by this function, that is e raised to the power minus x square, or the area bounded by this function, area bounded by this curve, is root pi. The fact is that it is a bell-shaped curve. It is not a circle, nor does it has any curvature of any circle. Still, the area under it is equal to root pi. This is a very surprising phenomenon, and we shall see why is it happening like this. So basically, this curve is called the bell-shaped curve. Bell-shaped curve. And it has got a great significance in statistics and probability. So let's see what is the solution of this integral and how is it happening over here. So first of all, we will consider this integral that is given equal to I. So I is equal to minus infinity to infinity e raised to the power minus x square dx. Now if I square it both the sides, then I have to write the same thing here also, because I am squaring, so I have to multiply it with itself. So it is minus infinity to infinity e raised to the power minus x square dx. Now over here, in place of x, if I write y, this also is okay. You can write y, no problem, no issues. Now, as per the rule of indices, as per the rule of exponents, we know that the powers having the same basis can be added. So I put all the integral operators to the one side, and e raised to the power minus x square plus y square means what I did, I added all the powers having the same base, that is e. So it is e raised to the power minus x square plus y square dx dy. Now the catch is that this dx dy, it is in rectangular coordinates, and for solving this we have to change it to polar coordinates, because in normal rectangular coordinates the solution of this integral is very difficult to obtain. So we will make a transformation and change it to polar coordinates. So for making this transformation from rectangular to polar coordinates, we need a special kind of operator that is called Jacobian operator. We need a special kind of operator that is called the Jacobian operator. It is represented as J. For the help of this Jacobian operator, means with the help of this Jacobian operator, we can easily write dx dy, that is this part, dx dy is equal to something Jacobian, that is the Jacobian, means for the transformation, the Jacobian operator that we will use, the value of the Jacobian that we will obtain, its determinant will be used to make the transformation from dx dy to dr d theta. So we can say that dx dy is equal to determinant of the Jacobian times dr d theta. So this is the transformation formula that we will use from rectangular coordinate system to polar coordinate system. So let's see how the transformation can be made. This is the rectangular coordinate system x. In the rectangular coordinate system, this is the origin. Now in the polar coordinate system, the same origin, we have another axis called the radius axis r, and this radius axis r starts from the origin and extends up to infinity. This is the radius axis, and this radius axis r is inclined at an angle theta with the horizontal. So this is the theta. So in the rectangular coordinates, we have two parameters, that is x and y. In the polar coordinates we also again have two parameters, that is r and theta. So how is this x, y and r theta related? We can say that x is equal to r cos theta and y is equal to r sin theta, where x square plus y square is equal to r square. So now we have the r and the theta coordinates also. Now let's see what is the range of r and theta. In this we see that the value of r is starting from 0 and ending up to infinity. So r will start from 0 and go up to infinity. And the theta value, that is theta, is starting from this horizontal, that is 0, and it will move in a circle because it is a degree. It is for denoting the degree, so it will move in a circle. So it starts from 0 and ends up to 2 pi, we can say. So this is the range of r and theta that we will use in the limit of integration. So now we will use the Jacobian. So Jacobian is equal to, the formula of Jacobian is del x comma y by del r comma theta. So this can be written as del x by del r del x by del theta del y by del r, sorry this is r, then del y by del theta. So this is the Jacobian matrix. We will find the value of del x by del r, del x by del theta. How? We have the value of x, we have the value of y. We will differentiate it in terms of r and theta and put the values over here. So we will obtain the Jacobian matrix as, that is del x by del r is equal to cos theta, del x by del theta is equal to minus r sin theta, del y by del r is equal to sin theta, and del y by del theta is equal to r cos theta. So this is the Jacobian matrix. If we find the determinant of this matrix, the determinant of this matrix is nothing but equal to r cos square theta plus r sin square theta. So this is equal to r, and in cos square theta plus sin square theta will itself be equal to 1, so we need not write that. Therefore we got the determinant of Jacobian is equal to r. So in this question, means in this previous part, in place of dx dy we can write determinant of Jacobian, that is r dr d theta, we can write. So here we will substitute as r dr d theta, this we can substitute. But wait a minute, you simply cannot write r dr d theta and do the calculation. We have to change the limit also. This limit will also change. Now this limit was for x, now this limit, now after changing this limit, that will become for the r. So this limit will go from 0 to infinity, and this limit will change from 0 to 2 pi. So this limit will change, this limit will change, and this dx dy will be transformed to r dr d theta. So after making all these implementations, after doing all these implementations in this integral, we will finally obtain I square is equal to 0 से infinity, again 0 से 2 pi e raised to the power minus r square r dr d theta. Now how is this minus r square coming? This r square is coming from this part, that is x square plus y square we had previously. Now instead of x square plus y square we will write r square from here. X square plus y square is replaced to r square and put over here, that is this one, this will be replaced to r square. Okay, so after making these implementations we will obtain I square is equal to 0 से infinity, 0 से 2 pi e raised to the power minus r square r dr d theta. Now here what we will do, here we will take minus r square is equal to u. Now du is equal to minus 2r dr. From here we can say that du by minus 2r is equal to dr. We will put this value of dr over here and see what are the changes happening. So I square is equal to 0 से infinity 0 से 2 pi e raised to the power u. Instead of dr we will write du by minus 2r d theta. Now this r and this r can be cut. This minus sign can be used to change this limit of integration from 0 to infinity. We can be written as minus infinity to 0. So we can write this as I square is equal to, the half I will bring outside because it is a constant. This minus sign will make this limit of integration to change, that is from minus infinity to 0, and from here 0 to 2 pi e raised to the power u du d theta. Now we will separate the integration operators for both the operands. It will become like I square is equal to half common. Now from minus infinity to 0 I will integrate e raised to the power u du, and from 0 to 2 pi I will integrate d theta, and this whole is multiplied with half outside the bracket. So upon doing this, that is I square is equal to half common. What we have inside, integration of e raised to the power u is e raised to the power u only. So it is from minus infinity to 0 multiplied with this one, integration of d theta is theta, and this, the limit of integration is from 0 to 2 pi. So we have to solve this one. So in the next slide I am doing it. So I obtained I square is equal to half times e raised to the power u from minus infinity to 0 into theta, that is from 0 से 2 pi, minus infinity to 0 and 0 to 2 pi. Yes. So now I will put the limits as upper limit minus lower limit. So it is half times upper limit is e raised to the power 0 minus e raised to the power minus theta times 2 pi minus 0. Now this I square is equal to half into e raised to the power 0 is 1 minus e raised to the power minus infinity is 0 into 2 pi. So this is equal to half into pi into 2 pi. This is equal to half into 2 pi. So this half 2 cancel, this half 2 cancel, this 2 cancel, so we will obtain pi. So we obtained I square is equal to pi. Therefore I is equal to root pi. This is the value of the integrand. So we have obtained that integration, that the value of the integrand is equal to root pi. This we have obtained, and this is what I was saying in the first slide. As you can see, this is what I was saying in the first slide, that the value of this integration, the area bounded by this curve, is coming to be root pi. As you can see in this figure also, I said earlier that it's come to be root pi. So what is the amazing and the most surprising thing about this? The fact is that this integration that was given to us, that is minus infinity to infinity e raised to the power minus x square dx, this integration that was given to us, the function fx is equal to e raised to the power minus x square, has a bell-shaped curve. It has a bell-shaped curve. So it has got great use in some of the following applications in statistics. It is used to denote the normal distribution that occurs naturally in many substances. So this bell-shaped curve, that is fx is equal to e raised to the power minus x square, it is used to denote the normal distribution the normal distribution that occurs in the nature, the normal distribution that occurs in the nature. So what are the normal distributions that occurs in the nature? Like suppose if I want to find the range of, means I have to find the range of all the height of the students in my class. So in that you will see that the graph so obtained will be a bell shaped curve. How? Maybe some students, actually what happens, this part, the part around the first the part around the first standard deviation, as you can say, the this is the part around the first standard deviation, it will contain the 68% of the data. So this is the average area, means the average, all the height of the students in my class will be concentrated around this part. The students who are less than the average height will be concentrated around this part, and the students who are above than the average height will be concentrated around this part, but the average height of the class will remain in this center. So I can say that the average height of the students in my class can be 5.5 feet. So maximum students, those who are having their height around 5.5 feet, will get clustered around this mean, around this standard deviation, the first standard deviation. So that is why it is forming a bell shaped curve. Even if you want to check about the salaries of the employees, that also will form a bell shaped curve. Even if you see the coronavirus pandemic graph, if you see, there was the first wave came and then decreased, again the second wave came and it is decreasing phase. So you will see that the first wave that came, that also followed this normal distribution method, that is a bell shaped curve, and the second wave that the coronavirus is having is also following the bell shaped curve, that is the normal distribution function. So each and every phenomenon in this universe follows a normal distribution function. Even the performance of the students of a particular class after the examination, that will also follow the normal distribution function. Means some students will be above the average, some students will be below the average, and the average is the average marks of the class, and most of the students will secure around the average marks of the class. So I can say that in the general form of normal distribution can be said as fx is equal to 1 by sigma root 2 pi e raised to the power minus 1 by 2 x minus mu by sigma the whole square. So this is the standard form of normal distribution function, where mu is the mean, or you can say the expected value, sigma is the standard deviation, and sigma square is the sigma square can be said as the variance. How much is it varying from the expected mean, that is the variance. Standard deviation is the amount of the amount it is varying, and mu is the mean, that is the expectation. So this is the normal distribution function. This is the general format of the normal distribution function. The main properties of this normal distribution function is that the mean, median, mode are all equal. In this kind of distribution curve, you will see that the mean, median, mode are all equal. They are symmetric around the center. As you can see, if this is the center, then they are symmetric. That is, on the left and right, they are both symmetric. And the standard normal deviation has mu equal to 0. The standard normal deviation will have mu equal to 0, and the sigma, that is the standard deviation, is equal to 1. This is for the standard normal distribution. This value is followed. And also I want to say that 68% of the data in any kind of distribution will always follow the first standard deviation, will be around the first standard deviation. 95% of the data falls under the second standard deviation, and the 99.7% of the data will fall under the third standard deviation. So what is the standard deviations? Let me draw it again. This time the standard deviation means suppose this is the bell shaped curve, This is the bell shaped curve. The first standard deviation will be around the mean. So this point is the mean, you can say, or the point where most of the data is clustered. That is this standard deviation. This is sigma 1, and this is the first standard deviation, as you can see, that is first sigma or minus 1 sigma. This is the second standard deviation, that is minus 2 sigma, and this is the, oh my god, what happened? And this is the third standard deviation, that is third sigma, minus 3 sigma, and this is the 3 sigma. So you will see that most of the data, that is most of the data will be clustered around this part, that is among between the first standard deviation. Most of the data is clustered around this first part, that is the first standard deviation. So how much data is clustered? That is 68% of the data will be clustered around this first standard deviation, and 95% of the total data will fall under the second standard deviation, that is from this part to this part. So this much is the first standard deviation, this much is the second standard deviation, and this much is the third standard deviation. So in the first standard deviation 68% of the data will fall, in the second standard deviation 95% of all the data will fall, and in the third standard deviation, that is 99.7% of the data will fall. So this is how a bell-shaped curve is useful in day-to-day life. Also, this bell-shaped curve is used in financial mathematics also. In financial mathematics, I have seen sometimes they use to predict the securities, means the return of securities and investments, the market flow, the capital flow, and the volatility of the market. All these things can be predicted by the bell-shaped curve. Even the customer relationship, the customer behavior, that a customer will buy a particular product or not, the brand reputation, all these kind of terms can be well defined by this bell-shaped curve. I hope you like this video. I made a small effort to make understand how this bell-shaped curve is highly applicable. If any suggestions, then please tell me how to improve my videos. Thank you.